For our first and only objective here, we are going to be able to apply a L'Hopital's rule to evaluate limits. And now specifically, these limits have to be of the form 0 over 0 or some kind of infinity over infinity, plus or minus infinity over infinity. And that's what the picture's showing us here with these cute little egg toys. You can see, depending on how you look at it, a 0 over 0 or an infinity over infinity. It's just that those infinities are rotated 90 degrees for some reason. I don't know. Okay, so as we saw from that third warm-up exercise, when we had the ratio of our two functions approaching 0 over 0, we got the indeterminate form 0 over 0, then that limit was equal to the ratio of the slopes at that particular pointer, approaching that particular point. So the reason why is because we are right around that little point and we are approximating our function with its local linear approximation, its tangent line approximation, right? Okay, so let me show you then where at least a part of this L'Hopital's rule comes from. It's kind of generic in general, and it looks like this. So we are going to make the following assumptions. We're going to assume that the limit as x approaches a of f of x approaches 0, and the limit as x approaches a of g of x is equal to 0. This is going to give us this whole limit as x approaches a of f of x divided by g of x. That's going to give us our 0 over 0 indeterminate form, which we need for L'Hopital's rule. So at x is equal to a, here are two local linear approximations for each one of these functions, right? So the tangent line, we have our y value, the f of a and the g of a, and the a where we're evaluating the function at. And then, of course, here's the slopes at each one of those two things, right? Okay, so then we're going to take our limit. It's going to be just like that I did in that example 3, that warm-up exercise, but we're doing it with these f of x, g of x kind of generic functions. So we're going to take the f of x out and we're going to replace it with its local linear approximation, which is valid around x is equal to a. We're going to do the same thing for the g of x function, right? And then remember that as x approaches a here, as x approaches, come on, laser pointer, where are you? As x approaches a, what happens with this f of a? What happens with this g of a? That's 0. These things go to 0, so they cancel out. They're gone. Why did that go to? Okay, so this, I can just cancel it out like that. All right, and then we're left with this guy right there. And then what happens? Well, the x minus a is on the top and the bottom. There's our hole. It disappears, it cancels out once again, and then I have the limit as x approaches a of f prime of a over g prime of a. This, my friends, is L'Hopital's rule. So the strategy here is you first try to do your direct substitution as always, and you see if you have the indeterminate form 0 over 0. This also works with infinity over infinity. And if you do, you just take the derivative of the top and the bottom, and then try again. Right? Again, this is called L'Hopital's rule. If f and g are differentiable on an open interval containing a, except possibly at a, why does it have to be differentiable? Because L'Hopital's rule is telling us to take the derivative of the top and the bottom. So, of course, it has to be differentiable. If the limit as x approaches a produces the indeterminate form 0 over 0 or infinity over infinity, or you can have the negative sign thrown in there someplace, then we have the limit as x approaches a of f of x over g of x is going to be equal to the limit as x approaches a of f prime of x over g prime of x. You just take the limits of the top and take the limit of the bottom. This is not the quotient rule. No. You take did I say the limit? I probably did. So you take the derivative of the top, you take the derivative of the bottom, exactly what you wanted to do whenever we were first learning how to do the quotient rule, which doesn't work. It does for L'Hopital's rule. That's very nice. Okay. And again, provided that this limit exists. So the handsome gentleman over here on the right-hand side, that is Guillaume, which is French for William L'Hopital, who is the one that is given credit for L'Hopital's rule. You can see this date here is 1696. This is shortly after Newton published his work, the Principia, which is the main work on calculus. That guy and who's the other one? Leibniz, right? Merci, Monsieur Bernoulli. Hey, what's that all about? Well, that is about the controversy which surrounds L'Hopital's rule. Now, here's the thing. I'm going to pull up Wikipedia here. There's Guillaume again. And He is known for this rule that we're about to talk about and about to use. And not only that, he's also known for writing the first calculus textbook. Where is it? Oh, here's some pictures for a minute. Ooh, look at that. Here's your, in this figure 5, so 5, that's 8. Yes, you can see an X and Y axis there. Looks like he didn't have access to a ruler. Okay, anyway, so here's his first calculus textbook. And it only did with derivatives, right? Derivatives and limits. It didn't have any integrals. Why is it controversial? Well, whenever he first published it, he didn't put his name on it, but he did in the acknowledgments acknowledge at least one person, and that was Bernoulli. So as it happens, he attended, and by he I mean Guillaume L'Hopital, attended some lectures given by Bernoulli, and he was so intrigued by these lectures, which was about calculus, he entered in this contract, this agreement with him. With Bernoulli's like, okay, so I'm gonna pay you 300 francs. If you don't know what francs are, that's the like French equivalent of a dollar-ish kind of thing. I'm going to give you 300 francs per year to give me all your mathematical discoveries, right? And so he did. And one of those things was L'Hopital's rule. And he assembled all of this stuff into the book. And this, what is this book called? It's called Infinitesimal Calculus with Applications to Curved Lines. So again, it was about just differentiable calculus. Okay, so after L'Hopital died, I hope Netflix, are you guys listening to this? This needs to be your next limited series. This is really good stuff. People will watch this. Anyway, so after L'Hopital died, Bernoulli came out and was like, hey, this was really my book, right? This is all my stuff. And everybody's going, no, it wasn't, man. But later, like historically, they found some evidence that it was probably true. So they found evidence of Bernoulli's lecture that L'Hopital attended, where he actually was basically everything that was in this textbook here, right? Anyway, okay, so that brings us to L'Hopital's rule. That was a nice little historical aside. So maybe, so here's Bernoulli right here, one of the two Bernoulli brothers, hotheads apparently. Like I said, man, fantastic Netflix series. Are you listening? Please put it together. Okay, maybe that should be L'Hopital's rule. And usually that's how I write it because I think it's funny. We put it in quotation marks. L'Hopital's rule. Some people actually call it Bernoulli's rule after all of this stuff came to light. Okay, so one of the T-shirt designs that I came up with a couple years ago makes fun of this, and I thought it was pretty clever. Here, you take a look at it. It's on this this alternative girl here with all her tattoos. Looks fantastic on her, doesn't it? Indeterminately paying bros to do my math homework since before you came out of Le Hospital. Oh, it's hilarious. It's hilarious. Okay, so a couple last things here. When you're using L'Hopital's rule, remember it's derivative over derivative. You take the derivative of the top, you take the derivative of the bottom. You do not use the quotient rule. You use the quotient rule, you're going to get the wrong answer. Okay. And as I said, this can be extended to infinity, like limits at infinity, and also one-sided limits. L'Hopital's rule will work as well. So let's take a look then at each one of these exercises that we started with right here using L'Hopital's rule. All right, I need some space to work. Back over here should do the trick. See, there was kind of a French accent, just a little bit. Okay, so we know that this goes to 0 over 0, which means that it is okay for L'Hopital's rule, quotation marks, right? And I do want to make that declaration if I do have to do this on a free response question. So I'm going to take the derivatives of the top and the bottom, limit as x goes to -1. Derivative of the top is a 4x. The derivative of the bottom is just a 1. And now whenever I directly substitute in a -4, I get a -1, I get a -4, which is what we got before, I do believe. Okay, so number 2 here gives us the infinity over infinity, which is a check for L'Hopital's rule. Once again, throw in your quotation marks if you want. So let's take some derivatives. Limit as x approaches infinity. Take the derivative of the top. I would have 6x over, take the derivative of the bottom. I'd have 4x. with some cancellation, I get 6 over 4, which reduces to 3/2. Now, it is entirely possible whenever you're using L'Hopital's rule that you have to use it more than once. So if you use L'Hopital's rule and you get an indeterminate form, you take the derivatives again until all the indeterminate forms disappear. Now, notice that I could have done that right here because this does, if I don't cancel out the x's, I would have infinity over infinity once again. So I take the derivative and I do get 6 over 4, which, yeah. Okay, so one last one. We have that 0 over 0, which was a check for L'Hopital's rule once again. So now I take the derivative of the top, take the derivative of the bottom, limit as x goes to 0. I would have 2e to the 2x over 1. Direct substitution here. I have is equal to 2e to the 0 power, which is just 2. Yes, yes, and yes.